Continuing on in section 1.5, we can join two inequalities with the word and or the word or to form a compound inequality. To solve a compound inequality containing and, we find all the values of the variable that make both inequalities true. We can also combine a compound and inequality into a single inequality. So, in example 5 here, we're going to find the solution and then graph it. So, first thing I'm going to do is I'm going to solve each inequality individually. When we write our answer, we have got to include the and or the or. They mean very different things about our solutions. So we have to explicitly state that so other people that are looking at these know what our answer means. So here I have 3 is less than x and x is less than or equal to 6. So we want all the numbers that 3 are less than and that are also less than or equal to 6. If we wanted to, we could write this as one compound inequality. It has to be a true statement, and it has to go the way that a number line would. So 3 is less than all of our numbers, and our numbers are less than or equal to 6 in our solution. So we could write it either of those two ways. And again, this only works with and inequalities because it has to work for both. As far as the graph goes, I'm going to put our boundary points on. We want 3 to be less than x. So 3 is less than 4, for example. We want x to be less than or equal to 6. And remember, our x is our solutions. That's just the part we shade. That's anything that makes it true. So x less than or equal to 6 are things like 5. So we're going to shade to the left of 6, to the right of 3, and only where they overlap. And then don't forget that we have the equal to with the 6, so that circle gets filled in as well. If we look from our compound inequality written as 1, what we're saying is x is in between 3 and 6. So we'd shade here in between. And then obviously our numbers on each side in 0, but that's what we're getting at there. Feel free to pause here and give this a try. First thing I'm going to do is I'm going to solve each inequality individually. Try that again. Divide by 2. And again, bring down our and or our or. They tell us how we're relating these two inequalities, and that's important. So I have 2 is less than or equal to x, and x is less than 6. So 2 is less than all of our numbers, and our numbers are less than 6. So I can write this as x is in between 2 and 6, 2 included with the equal. Either one of those ways works. On our graph, circle at 2, fill it in. Circle at 6, keep it open. 2 is less than our numbers, so 2 is less than 3, for example. And x is less than 6, so 5 is less than 6. We're going to go to the right here, to the left here, and where they overlap is our solution. Or again, we could say that x is in between 2 and 6. So it's in between there. One more thing with compound and inequalities. Occasionally we'll have something written like 6 is less than x plus 7, less than 10. You could either split this up and solve it as two inequalities, or whatever we do to one piece, we do to every piece. If I subtract 7 from the middle to get x by itself, I have to do that to both ends as well. So I get -1 less than x less than 3. Okay, whatever we do to the middle, we have to do to every part of our inequality. So here there's 3 parts, we do it to all 3. To solve a compound inequality containing or, we're going to find all the values of the variable that make at least one of the inequalities true. Here they don't have to work for both, they just have to work for at least one of them. So I'm still going to solve each individual inequality. Okay, greater than or equal to -1. Okay, less than -5. And we need the or here. Again, we have to say, how are these related? How do they go together? We want numbers that are greater than or equal to -1 or numbers that are less than -5, which is good because an and here would give us no solution. There are no numbers that work for both. So we have to make sure we have that or to say that there's still values included. -5 and our points on each side. -1 and our points on each side, and then we know where 0 is already here. Put a circle at -1. I'm going to fill it in because of the equal to. And we want numbers greater than or equal to -1. So numbers like 0, for example. Because it's an or, I graph each individual inequality on the same number line, because if it works for one, that's fine. It doesn't have to work for both. Circle at -5 to signify it's a boundary point. We want numbers smaller than -5, like -6. So we shade on the side that has our solution. And that is our graph. Feel free to pause here and give this a try if you'd like. First thing I'm going to do is solve each inequality for my variable. So W is greater than 8/7. Or W is less than -3. With ors, we can never ever write them as one single compound inequality like we did with ands where we combine them. We cannot do that with ors. -8/7. -3. We want numbers that are greater than 8/7, like 2. And numbers that are less than -3, like -4. And there we go. Here I'm going to change these so that they're both the same variable. That's my bad. So they're both x's. And solve. So 3 is less than x. Again, add or subtract first. Then multiply or divide to get that x by itself. And it's an or. So here, on my graph, I have 3 as a boundary point. I have -1 as a boundary point. For 3, I want 3 to be smaller than my numbers, like 4. Keep in mind here, guys, we didn't just match our arrow with our inequality because my variable wasn't first. If I wanted to do it that way, I need to switch this around so my variable's first. Alligator's eating X, it stays eating X. So X is actually greater than 3, and then I can match my arrow with my inequality. Here, I want numbers that are less than -1, like -2. And that is my solution. Again, with ORs, we cannot combine them into one inequality because there's no way to make that a true statement. There's no way to write, I want the same numbers to be less than -1 that are also greater than 3. We can't write that into one inequality and make it true because there are no numbers that work for both. Whereas in an AND, they have to work for both so we can combine it into one inequality. Quick recap here. Just as properties of equality can be used to solve equations, properties of inequality can be used to solve inequalities. Properties of numbers and inequality can be used to solve an inequality by finding increasingly simpler inequalities that have the same solution as the original inequality. And that's all I have for section 1.5.